everyone, I am Kenichi Miyaguchi from imec. I would like to present imec, a holistic approach to the curvilinear enablement for the advanced logic scaling from design to patterning. Let me start by explaining why the curvilinear patterning has attracted the significant interest in the advanced lithography and the design. First, printed pattern on both the mask and the wafer are inherently curvilinear in nature. Although IC layouts are traditionally represented using the Manhattan geometry composed of straight lines and right angles, the actual printed image is shaped by diffraction imaging optics and resist processes, resulting in smooth and continuous contours. In other words, the manufacturing process naturally produces the curvilinear features. Second, curvilinear design can improve the design mask wafer fidelity. With conventional Manhattan layouts, substantial OPC corrections are often required to compensate for imaging distortions. By allowing the curvilinear geometries in the design itself, the intended pattern can more closely match the final printed shape, reducing the gap between the design intent and the manufactured reality. Third, the curvilinear masks can enhance the lithographic performance. Smooth mask contours can improve the image formation, leading to larger the process window, reduce the pattern variability, and the potentially lower exposure dose requirements. These benefits become increasingly important as feature size approaches the resolution limits of the current lithography systems. Finally, curvilinear physical design may offer the additional design level advantages. The increased geometric flexibility can simplify the inter-cell routing, enabling the more efficient use of the layered space. In addition, smoother routing passes and fewer sharp corners may help reduce the parasitic effects and improve the electrical performance. Overall, curvilinear technology provides opportunities across the entire patterning ecosystem, from design, mask optimization to lithographic performance, and ultimately the circuit implementation. Okay, and beyond the lithography, the curvilinear technology may also bring the significant benefits to the physical design. This slide compares the conventional one-dimensional Manhattan layouts on the left with the two-dimensional curvilinear implementation on the right. In the Manhattan design, routing is constrained to horizontal and vertical direction, which often requires multiple metal layers, additional vias, and longer signal passes. These constraints increase the parasitic resistance and capacitance, ultimately impacting the circuit performance. In contrast, the curvilinear approach provides a greater routing flexibility. Signal paths can follow the smoother and more direct trajectories, reducing the routing distance and, in some cases, eliminating unnecessary vias. As a result, improvements in the power efficiency and the circuit performance are expected. Another potential advantage is area scaling. By utilizing routing resources more efficiently, curvilinear layouts may enable a reduction in the standard cell height. For example, from now 5 tracks to the 4 tracks, while maintaining the same gate pitch and the design rule. This translates directly into the higher logic density. Finally, the simplified routing structure may reduce the process complexity and the manufacturing cost by lowering the number of the required patterning steps and routing resources. Overall, the curvilinear physical design represents an opportunity not only for the better lithographic printability, but also for improvements in the performance, density, and cost at the design level. Curvilinear technology cannot be enabled by a single optimization step. Instead, it requires a complete ecosystem from design, mask manufacturing, lithography, etching, methodology, and inspection. This slide summarizes an end-to-end workflow investigated in this study. Starting from the Curvilinear standard cell design and the design rules check, the flow proceeds through the Curvilinear OPC, source mask optimization, and the pupil mask web front optimization. The optimized mask is then manufactured and evaluated through the lithography and etching experiments, followed by the control-based metrology and inspection. The key message here is that each stage influences the others. For example, the design that improves the lithography performance may increase mask complexity, while the mask rule that improves manufacturability may limit the design flexibility. Therefore, the huge Curvilinear deployment requires the holistic optimization across the entire ecosystem rather than the local optimization of the individual modules. Okay, let's go to the design. So one of the most attractive the application of the Curvilinear design is routing simplification inside the standard cells. This slide that shows examples of the flip-flop implementation using the three different routing approaches. On the top, both M0 and M1 use conventional Manhattan routing. Because routing directions are restricted, additional beards and metal 2 layers are required to complete the connections. In the middle, the M0 becomes curvilinear while M1 remains Manhattan. Routing congestion is reduced and the dependence on the upper metal layer is partially alleviated. Finally, on the bottom, both M0 and M1 adapted the curvilinear routing style. In this case, routing becomes sufficiently efficient that metal 2 layer and V1 beard can be completely eliminated. This example demonstrates how curvilinear routing can reduce routing resources, simplify the interconnect structures, and potentially improve both area efficiency and electrical performance. So next, we investigate the benefit of the Curvilinear OPC. This figure compares edge placement error distribution obtained using the conventional Manhattan OPC and Curvilinear OPC. With Manhattan OPC, correction flexibility is limited by the discrete orthogonal geometry of the target pattern. As a result, localized EP hotspots often appear around the corners and complex transitions. Curvilinear OPC introduces a smooth edge transition and a larger solution space for the optimization. This allows optical correction to better match the desired contours. As shown here, the EP hotspots are substantially reduced, resulting in a more uniform error distribution. These results suggest that Curvilinear OPC can improve the pattern fidelity and reduce imaging sensitivity in advanced logic layouts. However, the Curvilinear OPC introduced an important trade-off between the optical performance and the data volume. The step size shown here represents the spacing between the neighboring vertices along the curvilinear contour. A smaller step size allows the contour to be represented more accurately, providing the greater flexibility for the OPC optimization. As shown in the EL and the dot plots, reducing the step size from 5 nanometer to the 3 nanometers improves process window performance. However, this improvement comes with a significant increase in the mask data volume. For example, the data volume becomes roughly an order of the magnitude larger than that of the conventional Manhattan layouts. Therefore, practical curvilinear OPC requires a balancing the lithography benefits against the computation cost, data handling requirements, and mask writing overhead. Here, we investigate the combination of the curvilinear design with advanced lithography optimization techniques. The study focuses on the tipped line structure, which are among the most challenged pattern in the advanced logic technologies. Compared with the rectilinear geometry as a reference, curvilinear connection exhibits improved exposure latitude and depth focus under the SMO conditions, as shown in the plots. The smoother contour reduces diffraction discontinuity and produces more stable area image. Further improvement is achieved when the pupil mask wavefront optimization is applied. The combination of the curvilinear geometry and the PMWO extends the achievable tip line design limit by approximately 6 nanometers, while maintaining the robust process window. These results demonstrate the strong synergy between the curvilinear design and advanced lithographic optimization techniques. So let's move to the mask. So for practical mask manufacturing, curvilinear layout requires a new mask rule methodologies. Traditional mask rules are primarily designed for the Manhattan geometries and fully captured the characteristic of the smooth curvilinear features. This slide proposes several of the essential curvilinear mask rule concepts. First, it's a projection length-based width and spacing definitions are introduced to evaluate the local geometric the constraint along the curved the contours. Second, in the middle, the maximum convex and concave curvature limits are defined to ensure the manufacturability of the curvilinear masks. Third, minimum hole and island area constraints are added to prevent unstable mask features. Together, these rules provide a foundation for the practical curvilinear mask verification and manufacturing. So then, to determine the manufacturable curvature limits, dedicated test structures were fabricated and analyzed. The structures consist of the oval-shaped patterns with varying the curvature radius. Comparing the design targets with the mass SEM measurements revealed that the curvature fidelity begins to degrade when the radius becomes smaller than approximately 10 nanometers. This degradation likely originates from limitation in the mask writing and the resist development and etching processes in the mask. Based on these experimental results, a practical curvature radius limit of roughly 10 nanometers is proposed for the investigated mask process. So, after establishing the curvature rules, using the test structures, we moved to evaluate the curvature methodology and the realistic use case logic metal patterns. This compares target contours and measured the mask contour for both the convex and the concave regions. The results shows a good agreement between the mask design and the manufactured the mask shapes. More importantly, curvature information can be quantitatively and extracted from the actual product-like layouts, and as shown here, it's mask SEM images. This capability enables the curvature-based process monitoring and may become the important component of the future curvilinear mask qualification methodology. So next, we validate the curvilinear pattern transfer on the wafer. The figure compares the original design targets, the lithographic results, and the final etched pattern. Using the 0.33 NA UV lithography, followed by the etching integration, smooth curvilinear contours are successfully transferred onto the wafer. The contour fidelity is largely maintained throughout the patterning process. These results demonstrate that curvilinear layouts are compatible with advanced UV lithography and etching flows, and can be realized experimentally at the wafer level. So in this slide, we analyze the relationship between the lithography and the etching bias. The figure compares the CD behavior for both the vertical curvilinear features and the horizontal features. You can see the similar trend and in both directions. This indicates that the etching process largely preserves the contour characteristics established during the lithography. In other words, the lithography to etch transfer behaves in a relatively conformal manner. Such conformal behavior is important because it allows the curvilinear shape generated during the lithography to be maintained through the final pattern transfer process, through the etch. So traditional process window analysis is typically based on the one-dimensional CD measurements. However, curvilinear layers contain the important two-dimensional content information that cannot be fully captured by the CD metrics alone. This slide compares conventional CD-based evaluation with the contour-based process window analysis. When only horizontal lines are analyzed, the process window behavior appears relatively conventional. However, when both the horizontal and the vertical curvilinear features are evaluated simultaneously, additional sensitivity becomes visible. These results highlight the importance of the contour-based methodology for the future curvilinear technology, where overall shape fidelity may be more important than the individual CD measurement. So that brings a conclusion. In conclusion, this work presents a comprehensive end-to-end approach for the curvilinear enablement. We investigated the curvilinear standard cell design, OPC optimization, including the SMO and PMW, mask rule developments, curvature methodology, and experimental lithography and etching demonstrations. The results show that curvilinear technology can provide benefits across multiple domains, including design flexibility, pattern fidelity, process window enhancement, and routing simplification. For future, we look forward, several challenges remain, including the defectivity control, inspection methodology, and more importantly, high-NA UV validation. Nevertheless, the results presented here demonstrate that curvilinear technology is a promising the pathway for future logic scaling and advanced patterning applications. Thank you for watching the presentation.